In this lecture, you are going to build the complete Agentic Observability pipeline from a single Node.js application through an OpenTelemetry Collector that scrubs sensitive data into Splunk and all the way to an AI agent that can query your data in natural language and open a pull request to fix a production incident. Let's get to work.
Welcome to Nextgen AI. This lecture is brought to you by author, innovator, and technology leader Juan Achurra. With over 25 years of experience designing AI strategies, SRE frameworks, and enterprise platforms for Fortune 500 companies and government agencies, Juan brings the kind of knowledge most organizations pay thousands of dollars to access. So grab your drink, open your mind, and get ready for the flow of knowledge. Let's get started.
OpenTelemetry is not just another monitoring tool. It is a fundamental shift in how we approach observability at the enterprise level. Historically, organizations were locked into proprietary agents. If you bought Splunk, you ran the Splunk agent. If you switched to Dynatrace, you had to rip out the Splunk agent and deploy the Dynatrace agent across your entire fleet. This created massive vendor lock-in and operational friction. OpenTelemetry, a cloud-native computing foundation project, solves this by standardizing how telemetry data, metrics, logs, and traces is generated, collected, and exported. It provides a single set of APIs, SDKs, and instrumentation libraries that work across almost every programming language. When you instrument your application with OpenTelemetry, you are writing vendor-neutral code. The data is emitted in the OpenTelemetry Protocol, or OTLP, which has become the universal language of observability. This means you can send your data to Splunk today, Datadog tomorrow, and Grafana the day after, all without touching a single line of application code. By adopting OpenTelemetry, you decouple your instrumentation strategy from your back-end analytics platform, giving your engineering teams the freedom to choose the best tools for their specific needs without the burden of re-instrumentation. To understand OpenTelemetry, you must understand the three pillars of observability: traces, metrics, and logs. While they are often discussed separately, their true power emerges when they are correlated. Traces track the progression of a single request as it travels through a distributed system. A trace is composed of spans, where each span represents a specific operation, like a database query or an API call, complete with start times, end times, and status codes. Metrics are aggregated numerical data points measured over time. They tell you about the overall health of your system: CPU utilization, memory consumption, request rates, and error percentages. Metrics are fantastic for triggering alerts, but they rarely tell you why an alert fired. That is where logs come in. Logs are immutable, time-stamped records of discrete events that happened within your application. The magic of OpenTelemetry is that it natively correlates these three pillars. When a trace is generated, OpenTelemetry automatically injects the trace ID and span ID into the corresponding log entries. This means when an alert fires based on a metric spike, an SRE can immediately pivot to the exact trace that caused the anomaly and then dive directly into the specific log lines emitted during that exact transaction. The OpenTelemetry data model is built on the concept of semantic conventions. When you operate a complex microservices architecture, consistency in how you name and structure your telemetry data is paramount. If one team labels their database queries as db.query and another team uses sql.statement, building unified dashboards or automated alerting rules becomes nearly impossible. OpenTelemetry solves this by defining a strict, standardized vocabulary for common operations. For example, any HTTP request span will always include attributes like http.method, http.statuscode, and http.target. Any database span will include db.system and db.statement. Beyond operation-specific attributes, OpenTelemetry also relies heavily on the resource object. The resource represents the entity producing the telemetry, the specific pod, container, host, or serverless function. By attaching a standardized resource object to every span, metric, and log line, OpenTelemetry ensures that your data is always context-rich. When an AI agent or an SRE investigates an issue, they do not just see a generic error, they see an error explicitly tied to a specific version of a microservice running in a specific Kubernetes namespace on a specific node. This structured, predictable data model is the absolute prerequisite for any effective AI ops or automated remediation strategy. One of the most significant barriers to adopting observability has always been the developer effort required to instrument code. Manually adding span creation, context propagation, and error handling to every business transaction is tedious, error-prone, and often neglected under tight deadlines. OpenTelemetry solves this brilliantly with auto-instrumentation. In the Node.js ecosystem, auto-instrumentation is achieved through a combination of the OpenTelemetry SDK and a suite of pre-built instrumentation plugins. You do not need to modify your application's source code. Instead, you create a single configuration file, typically named instrumentation.js, and you instruct the Node.js runtime to require this file before it boots your application. The auto-instrumentation libraries use monkey patching techniques to hook into the core Node.js modules and popular third-party libraries. The moment your Express server starts, OpenTelemetry is already listening. It automatically intercepts incoming HTTP requests, extracts any incoming trace context from the headers, creates a new span for the request, and injects that context into any outbound database calls or downstream API requests. This zero-code approach democratizes observability. It ensures that every microservice in your fleet, regardless of who wrote it or when it was deployed, provides a consistent, high-quality baseline of telemetry data from day one. Let us look at the actual code required to set up OpenTelemetry in a Node.js application. The entire configuration lives in a single file, typically named instrumentation.js. The core component here is the Node SDK object provided by the OpenTelemetry package. When you instantiate the Node SDK, you are configuring the entire observability pipeline for that specific Node.js process. First, you define the resource object, which identifies your service. You use the semantic resource attributes to set the service name, ensuring it aligns with the OpenTelemetry standards. Next, you configure the trace exporter. In a production environment, this is almost always the OTLP trace exporter, which formats the spans into the OpenTelemetry protocol and sends them over gRPC or HTTP to your OpenTelemetry Collector. Finally, and most importantly, you define the instrumentations array. By calling the getNodeAutoInstrumentations function, you are instructing the SDK to load the entire suite of official auto-instrumentation plugins. This covers Express, HTTP, GraphQL, PostgreSQL, Redis, and dozens of other common libraries. By centralizing this configuration in a single file, you keep your application's business logic completely clean and untouched by observability concerns. The instrumentation file simply wraps your application in a comprehensive telemetry net. Once your instrumentation.js file is written, the final step is to actually inject it into your Node.js application at startup. You do not import this file inside your application code. Instead, you use the Node.js command line --require flag. When you start your application, instead of running node-index.js, you run node-require./instrumentation.js index.js. This distinction is critical. By using the --require flag, you guarantee that the OpenTelemetry SDK is the absolute first thing that loads into the Node.js runtime before any other modules or application logic. This allows the auto-instrumentation libraries to successfully monkey patch the core HTTP and database drivers before your application has a chance to use them. If you were to import the instrumentation file normally inside your application, there is a high risk that some modules would load before the instrumentation hooks were in place, resulting in missing spans and broken traces. The --require flag ensures a clean, deterministic initialization sequence. This pattern is standard across the Node.js ecosystem and is the recommended best practice for deploying OpenTelemetry auto-instrumentation in production environments, whether you are running on bare metal, inside Docker containers, or orchestrated by Kubernetes. So, what exactly do you get for free when you enable auto-instrumentation? The amount of context captured without writing a single line of code is staggering. Every time an external client makes an HTTP request to your Express server, a root span is automatically created. This span captures the HTTP method, the exact route matched by Express, the full URL, the user agent, and the client's IP address. If that request triggers a database query, the auto-instrumentation library for PostgreSQL or MongoDB intercepts the call. It creates a child span linked to the root span and captures the exact SQL statement executed, the database name, the connection pool status, and the precise execution time of the query down to the millisecond. If the database throws an error, the span status is automatically marked as an error, and the full stack trace is attached to the span as an event. If your service then makes an outbound API call to another microservice, the HTTP client instrumentation creates another child span and automatically injects the W3C trace context headers into the outbound request. This allows the downstream service to continue the trace, creating a seamless, unbroken distributed trace across your entire architecture. When your instrumented Node.js application is running under load, the OpenTelemetry SDK is working continuously in the background. It is important to understand how it handles the telemetry data to ensure it does not impact your application's performance. The SDK does not send every span to the collector the millisecond it is created. That would cause massive network overhead and latency. Instead, it uses a batch span processor. As spans are completed, they're placed into an in-memory queue. The batch span processor periodically flushes this queue, sending a large batch of spans to the collector in a single network request. You can configure the maximum queue size, the batch timeout, and the export timeout to tune this behavior for your specific workload. If your application experiences a massive traffic spike and the queue fills up, the SDK is designed to fail gracefully. It will drop telemetry data rather than consume excessive memory or block the main Node.js event loop. Your application's primary function is to serve user requests, not to generate telemetry. The OpenTelemetry SDK respects this priority, ensuring that observability remains a lightweight, low-overhead addition to your production services. Before you route your telemetry to a production backend like Splunk or Dynatrace, you must verify that the instrumentation is working correctly locally. The easiest way to do this is to temporarily swap the OTLP exporter in your instrumentation.js file with a console span exporter. When you restart your application and send a few test requests, the OpenTelemetry SDK will print the fully formatted spans directly to your terminal. This is your opportunity to inspect the raw data structure. You should verify that the trace IDs and span IDs are generating correctly and that child spans are properly linked to their parent spans. Look closely at the attributes block. Ensure that the semantic resource attributes you configured, like the service name and environment, are present on every span. Check the HTTP attributes to confirm the status codes and routes are accurate. If your application interacts with a database, verify that the database statement is being captured without truncating critical information. This local validation step is crucial. It ensures that the telemetry data you are generating is structurally sound and semantically correct before it enters the complex processing pipelines of the OpenTelemetry Collector. Now that your application is generating telemetry, we need to talk about what happens to that data before it reaches Splunk. This is where the OpenTelemetry Collector becomes the most important piece of your observability architecture. The OpenTelemetry Collector is the architectural linchpin of a modern observability strategy. While you could configure your applications to send telemetry directly to Splunk or Datadog, doing so creates a brittle, tightly coupled architecture. The collector acts as a vendor-agnostic proxy and processing engine that sits between your applications and your analytics backends. It is built on a pipeline architecture consisting of three main components: receivers, processors, and exporters. Receivers define how data gets into the collector, typically via the OTLP receiver listening on gRPC or HTTP ports. Exporters define where the data goes, such as the Splunk HEC exporter or a Prometheus exporter. But the true power of the collector lies in the processors. Processors sit in the middle of the pipeline and allow you to mutate, filter, and enrich the telemetry data in flight. You can use processors to batch data for efficient network transfer, to add Kubernetes metadata to spans, to filter out health check noise, or to sample traces based on error rates. By centralizing this logic in the collector, you remove the burden of telemetry routing and formatting from your application developers, creating a highly scalable, flexible observability infrastructure. As we capture increasingly granular telemetry data, we introduce a significant risk: the accidental logging of personally identifiable information, or PII. When auto-instrumentation captures full SQL statements, HTTP payloads, or verbose error messages, it is incredibly easy for credit card numbers, social security numbers, passwords, or authentication tokens to slip into the telemetry stream. If this sensitive data reaches your observability backend, you have triggered a massive compliance violation. Splunk, Dynatrace, and Grafana are not designed to be secure vaults for regulated data. They are analytics platforms accessible by hundreds of engineers across your organization. Once PII is indexed in a system like Splunk, remediating the breach is a nightmare. You often have to purge entire indexes, destroying valuable operational data in the process, and you still have to report the compliance failure to auditors. Relying on developers to manually scrub PII in application code is a losing battle. Human error is inevitable. We need a systemic, automated defense mechanism that guarantees sensitive data never leaves the secure boundary of the application environment. This is where the OpenTelemetry Collector becomes a critical security tool. To solve the PII problem, we utilize the OpenTelemetry Collector's redaction processor. This processor acts as an automated compliance firewall. It sits directly in the collector's processing pipeline, inspecting every single span, metric, and log line before it is handed off to the exporter. The redaction processor is configured via the collector's YAML file, meaning your security policies are defined as code, version-controlled, and universally applied. You do not need to trust that 50 different development teams are correctly scrubbing their logs. You enforce the rules centrally at the collector level. The processor works by evaluating the telemetry data against a defined set of rules.
It can target specific span attributes, metric labels, or the raw body of log messages. When it finds a match, it mutates the data in flight, replacing the sensitive information with a safe placeholder, such as a string of asterisks or a cryptographic hash. Because the collector processes data in memory, this redaction happens in milliseconds, adding negligible latency to the telemetry pipeline while providing an absolute guarantee that PII will not leak into your downstream observability platforms. The most powerful feature of the redaction processor is its support for regular expressions. This allows you to define complex pattern matching rules to identify PII even when it is embedded deep within unstructured text, such as a stack trace or a verbose log message. In your collector YAML configuration, you define a list of blocked values. Each entry in this list is a regular expression designed to catch a specific type of sensitive data. For example, you can write a regex to identify the standard format of a U.S. Social Security number, or the 16-digit pattern of a Visa or MasterCard. You can define patterns to catch email addresses, API keys, or JWT tokens. It is critical to wrap these regular expressions in single quotes within the YAML file to prevent parser errors with special characters. When the redaction processor scans a span or log line, it applies every regex in the blocked values list. If a pattern matches, the processor automatically replaces the matched text with a mask, typically 5 asterisks. This regex-based approach ensures that PII is scrubbed regardless of the context in which it appears, providing a robust defense against accidental data leakage. While regular expressions are excellent for unstructured text, much of the data handled by OpenTelemetry is highly structured, consisting of key value pairs in span attributes or log contexts. The redaction processor handles this structured data efficiently through key-based masking. In the YAML configuration, you can define a list of allowed keys or blocked keys. If you know that a specific attribute, such as user.password or http://request.header.authorization, will always contain sensitive data, you simply add that key to the blocked keys list. The processor will immediately mask the value associated with that key without needing to run a complex regex evaluation. Conversely, you can use the allowed keys list to enforce a strict allow list policy. If an attribute key is not explicitly listed in the allow list, its value is automatically redacted. This is a highly secure default deny approach. Key value masking is significantly faster than regex evaluation, reducing the CPU overhead on the collector. By combining targeted key-based masking for structured attributes with regex-based masking for unstructured log bodies, you create a highly optimized, comprehensive redaction strategy. Simply masking PII with asterisks solves the compliance problem, but it creates an operational problem. If an SRE is investigating a bug that only affects a specific user, and that user's email address is masked as 5 asterisks, the SRE cannot trace that user's journey through the logs. Every user's email looks exactly the same. The redaction processor solves this elegantly by supporting cryptographic hashing. Instead of replacing the matched PII with asterisks, you can configure the processor to replace it with a SHA-1 or SHA-3 hash. When hashing is enabled, the processor takes the sensitive string, like an email address, and runs it through the cryptographic algorithm, producing a unique, irreversible alphanumeric string. Because the hash is deterministic, the same email address will always produce the exact same hash value. This means the PII is securely anonymized, completely satisfying compliance requirements. But the SRE can still use the hash value as a unique identifier to correlate logs and traces for that specific user across the entire distributed system.
Hashing preserves the operational utility of the telemetry data while completely neutralizing the security risk. Configuring the redaction processor is only the first step. Validating that configuration is an absolute necessity before deploying to production. A single typo in a regular expression can render your compliance firewall useless. To validate the setup, you must intentionally generate test telemetry that contains dummy PII, fake credit card numbers, test email addresses, and mock API keys. You then configure the OpenTelemetry Collector to use a local logging exporter, which prints the processed telemetry data directly to the console instead of sending it to Splunk. You must manually inspect this console output. Verify that the dummy credit card numbers in the HTTP payloads have been replaced with asterisks. Confirm that the test email addresses in the span attributes have been correctly transformed into SHA-3 hashes. Look closely at edge cases. What happens if the credit card number has dashes instead of spaces? Does the regex still catch it? What if the API key is embedded inside a larger JSON string within a log message? Rigorous intentional validation is the only way to guarantee that your redaction rules are bulletproof and that your organization is protected from catastrophic data leaks. With our telemetry data successfully generated by auto-instrumentation and securely scrubbed by the redaction processor, it is time to export it to our analytics backend. In this curriculum, our target is Splunk, and the mechanism we use is the Splunk HTTP Event Collector, or HEC. The Splunk HEC is a highly scalable, robust endpoint designed specifically to ingest massive volumes of machine data over HTTP or HTTPS. It is the industry standard for routing high-velocity telemetry into Splunk indexes. The OpenTelemetry Collector includes a native Splunk HEC exporter. This exporter is incredibly powerful because it automatically translates the standardized OpenTelemetry protocol data, the spans, metrics, and logs, into the specific JSON payload structure that the Splunk HEC endpoint requires. You do not need to write custom parsing scripts or translation layers. You simply configure the Splunk HEC exporter in your collector YAML file, provide the endpoint URL, and the collector handles the complex serialization process seamlessly. This native integration allows you to leverage Splunk's industry-leading search and analytics capabilities using purely open-source, vendor-agnostic OpenTelemetry data. Authentication with the Splunk HEC is handled via token-based security. You do not use usernames and passwords to send data to the HEC endpoint. Instead, you generate a unique cryptographic token within the Splunk interface. This token is a highly sensitive credential. If a malicious actor gains access to your HEC token, they can flood your Splunk indexes with garbage data, driving up your ingestion costs and blinding your operational dashboards. Therefore, you must never hard-code the HEC token directly into your collector's YAML configuration file. Doing so would expose the token in your version control system, a critical security failure. Instead, you must use environment variable substitution. In the YAML file, you reference the token using the $env: Splunk_HEC_token syntax. When the collector boots up, it reads the actual token value from the secure environment variables of the host machine or the Kubernetes secret store. This pattern ensures that your infrastructure as code remains clean, shareable, and completely devoid of hard-coded secrets. The final step in configuring the OpenTelemetry Collector is wiring the components together using pipelines. You have defined your OTLP receiver, your redaction processor, and your Splunk HEC exporter, but they do not do anything until they are explicitly linked in the service section of the YAML file. The collector allows you to define separate pipelines for traces, metrics, and logs. This is a critical architectural feature. It means you can apply different processing rules to different types of data. For example, you might want to run the redaction processor on traces and logs, but skip it for metrics to save CPU cycles, since metrics rarely contain PII. In our configuration, we define a traces pipeline that starts with the OTLP receiver, passes the data through a memory limiter, routes it through the redaction processor to scrub the PII, batches the data for network efficiency, and finally pushes it out through the Splunk HEC exporter. The order of processors in the pipeline matters immensely. You must ensure that the redaction processor executes before the batch processor. Otherwise, you risk exporting sensitive data before the compliance rules have a chance to evaluate it. Once the collector pipeline is running and the Node.js application is under load, the ultimate validation happens inside Splunk. You must log into the Splunk search head and execute a query against the index you configured for the HEC token. The goal here is not just to see if data arrived, but to verify its structural integrity. You should see the OpenTelemetry spans represented as individual Splunk events. Check the Fields sidebar to confirm that the OpenTelemetry semantic attributes like http.method, http.status-code, and service.name have been correctly parsed and extracted by Splunk. Verify that the timestamps align with the actual event generation time, ensuring there is no significant ingestion latency. Most importantly, you must verify the success of your redaction processor. Search the index for the dummy PII patterns you generated during your local testing. If your redaction rules are working correctly, those searches should return 0 results, and you should only see asterisks or cryptographic hashes in the raw event text. This final end-to-end verification confirms that your entire observability pipeline is secure, compliant, and ready for production workloads. We have successfully instrumented our application and routed the data to Splunk. Now we must address how we actually use that data to detect problems. Historically, setting up alerts in platforms like Splunk or Dynatrace involved a practice known as ClickOps. An SRE would log into the web interface, navigate through a series of menus, manually type in a search query, set a threshold using drop-down boxes, and click Save. This manual approach is fundamentally broken for modern scale-out architectures. ClickOps is untrackable. There is no audit trail of who changed an alert threshold or why. It is unrepeatable. If you need to deploy the exact same alerting rules to a new staging environment, you have to manually click through the UI all over again. And it is incredibly fragile. A single accidental click can disable a critical production alert without anyone noticing until an outage occurs. As infrastructure has moved toward declarative, version-controlled code, our observability and alerting strategies must evolve to match. We cannot manage cloud-native telemetry with manual UI clicks. The solution to the ClickOps problem is monitoring as code, or MAC. Monitoring as code applies the exact same engineering rigor and automation principles to your observability stack that infrastructure as code applies to your cloud deployments. Instead of clicking through a web interface, you define your dashboards, your search queries, and your alerting thresholds in declarative, human-readable configuration files, typically YAML or JSON. These files are treated as first-class source code. They are stored in a Git repository alongside your application code. This fundamental shift transforms observability from a manual operational task into a disciplined software engineering practice. When your alerts are defined as code, they become version-controlled, auditable, and easily deployable across multiple environments using standard CI/CD pipelines. Monitoring as code ensures that your observability posture is deterministic and reproducible, eliminating the configuration drift and human error inherent in manual UI management. Let us look at what monitoring as code looks like in practice. In the Prometheus ecosystem, alerts are defined using a YAML structure called a Prometheus rule. This file contains the exact PromQL query used to evaluate the metric, the threshold that triggers the alert, and the duration the condition must persist before the alert fires. It also includes annotations that define the severity of the alert and the routing tags used by the alert manager to page the correct team. In Splunk, alerting rules are defined in a file called savedsearches.conf. This file contains the raw SPL query, the cron schedule that dictates how often the query runs, and the specific actions to take when the threshold is breached, such as sending an email or triggering a webhook. By defining these rules in flat text files, you completely decouple the logic of your alerts from the proprietary web interface of the vendor. The YAML or conf file becomes the single source of truth for your monitoring logic, ensuring absolute clarity and transparency for the entire engineering team. The true power of monitoring as code is unlocked when you combine it with a GitOps workflow. GitOps makes the Git repository the absolute center of gravity for your operational state. If an SRE determines that a CPU alert threshold is too sensitive and is causing alert fatigue, they do not log into the Splunk UI to change it. Instead, they open a pull request in the monitoring repository, modifying the specific YAML file. This pull request serves as a formal proposal for the change. It triggers automated CI tests, perhaps a linter to verify the YAML syntax, or a script to validate that the SPL query is well-formed. The pull request requires approval from a peer, ensuring that no single engineer can alter production alerting without oversight. Once the PR is approved and merged into the main branch, a CD pipeline automatically detects the change and pushes the updated configuration directly to the Splunk or Prometheus API. This workflow creates an immutable audit trail, enforces peer review, and guarantees that the production alerting state always perfectly matches the code in the repository. Why are we emphasizing monitoring as code in a curriculum focused on agentic AI? Because AI agents cannot interact with web interfaces. An AI agent cannot click through the Splunk UI to adjust an alert threshold. AI agents interact with systems through APIs and text files. If your observability posture is locked behind a proprietary UI, your AI agent is blind and paralyzed. However, if your alerts, dashboards, and routing rules are defined as YAML files in a Git repository, the AI agent can read them, understand them, and most importantly, modify them. When an incident occurs, an AI agent can analyze the telemetry, determine that a threshold needs to be adjusted, and automatically generate a pull request modifying the specific YAML file. Monitoring as code is the foundational prerequisite for agentic SRE. It transforms your observability infrastructure into a programmable surface area that intelligent agents can navigate and manipulate with precision. When defining alerts as code in Splunk, the core of the configuration is the Search Processing Language, or SPL, query. Writing efficient SPL is critical because these queries run continuously in the background on a cron schedule. A poorly optimized query can consume massive amounts of CPU on your Splunk search heads, degrading performance for the entire organization. When writing SPL for an alert, you must always start with the most restrictive filters possible. Specify the exact index, the exact source type, and the narrowest possible time window. Do not use leading wildcards, as they force Splunk to scan the entire index. Use the stats command to aggregate data efficiently before applying conditional logic with the where command. For example, to calculate an error rate, you should use stats count as total count and count of eval status greater than 500 as error count, and then use eval error rate equals error count divided by total count. This approach is significantly more efficient and accurate than trying to count absolute errors, as it accounts for natural fluctuations in overall traffic volume. A critical aspect of monitoring as code is enforcing standardized alert metadata. When an alert fires at 3 a.m., the responding SRE needs immediate, actionable context. If the alert just says, "High CPU," it is useless. Your saved searches.conf files must enforce strict naming conventions and include comprehensive metadata. Every alert must clearly define its severity. Is it a SEV1 critical outage or a SEV3 warning? It must include the specific routing tags that dictate which team receives the PagerDuty notification. Most importantly, every alert defined in code must include a direct link to the corresponding runbook. The runbook provides the step-by-step remediation procedures for that specific failure mode. By embedding the runbook link directly into the alert configuration code, you guarantee that the responder has immediate access to the documentation they need the moment the pager goes off. This standardization drastically reduces mean time to resolution and prevents the chaos of searching for documentation during a critical incident. While traces and metrics provide deep visibility into internal application state, you also need an external perspective. Synthetic health checks provide this by simulating user traffic from outside your infrastructure. A health check is a script that periodically pings your application's public endpoints, verifying that the service is reachable, that the TLS certificates are valid, and that the endpoint returns the expected HTTP 200 OK status code within a defined latency threshold. These checks are critical because your internal metrics might look perfectly healthy, even if a misconfigured load balancer or a DNS failure is preventing users from accessing the site. By configuring synthetic health checks as code and routing their results into your OpenTelemetry pipeline, you create a holistic observability posture that combines deep internal diagnostics with objective external availability metrics. This ensures that your alerting strategy accurately reflects the actual experience of your end users.
We have spent the first half of this lecture building the data pipeline. We instrumented a Node.js application with OpenTelemetry, we routed the telemetry through a collector that scrubs PII using the redaction processor, and we exported clean, structured data into Splunk via the HTTP event collector. That pipeline is the foundation. Now we are going to build the intelligence layer on top of it. The question we need to answer is, how do we connect the analytical power of a large language model to the live telemetry data sitting inside Splunk? The answer is the Model Context Protocol, or MCP. MCP is an open standard, originally developed by Anthropic, that defines a secure, structured communication channel between an AI agent and external data systems. Think of it as a universal adapter. Instead of building a custom integration between Claude and Splunk's API, you deploy a Splunk MCP Server, which speaks both languages fluently. The AI agent sends standardized tool requests to the MCP server, which translates them into native Splunk API calls, executes them, and returns the results in a format the LLM can reason over. This bridge transforms Splunk from a passive data repository into an active, queryable intelligence layer for your AI agent. To implement the Splunk MCP integration correctly, you need a clear mental model of the architecture. There are three distinct layers. The first layer is the AI client, in our case, Claude Desktop, or a custom agent built with the Anthropic API. This is the reasoning engine. It receives user questions, breaks them down into subtasks, and decides which tools to call. The second layer is the Splunk MCP Server. This is a lightweight application that runs as a separate process, either on your local machine or on a dedicated server in your network. It exposes a set of named tools, like execute SPL, list indexes, and get alert status, that the AI client can discover and invoke. The third layer is your Splunk Enterprise or Splunk Cloud instance. This is where the actual data lives and where the searches are executed. The MCP server holds the Splunk credentials and manages the authenticated connection to the Splunk REST API. The AI client never touches Splunk directly. This three-layer separation is critical for security. It means you can grant the AI agent access to specific Splunk capabilities without ever exposing your Splunk admin credentials to the LLM or to the end user.
The Splunk MCP Server is distributed as an official application through Splunkbase, which is Splunk's curated app marketplace. The installation process follows the same workflow as any other Splunk app. You log into your Splunk web interface as an administrator, navigate to the Apps menu, and click the option to browse more apps. In the Splunkbase search bar, you search for the Splunk MCP Server application. You will find the official listing published by Splunk. You click Install and authenticate with your Splunkbase credentials to authorize the download. Splunk will automatically download the application package and install it on your search head. After the installation completes, you will see the Splunk MCP Server listed in your Apps menu. The application registers itself with the Splunk platform and creates the necessary REST API endpoints that the MCP client will communicate with. It also creates the required Splunk roles and capability definitions that you will use in the next step to configure role-based access control. The entire installation process takes less than 5 minutes and requires no manual file copying or command line operations.
Security is the most critical configuration step in the entire MCP integration. The Splunk MCP Server needs a dedicated service account, a Splunk user that exists solely to execute searches on behalf of the AI agent. You must never use an admin account or a personal user account for this purpose. Log into Splunk as an administrator and navigate to Settings, then Users. Create a new user account with a descriptive name like MCP Service Account. Assign this user a custom role that you create specifically for MCP access. In the role definition, grant only the two capabilities the MCP server requires: MCP Tool Execute for running standard searches, and MCP Tool Admin only if you need the agent to manage saved searches. Critically, you must explicitly define which indexes this role can search. Grant access only to the indexes containing your OpenTelemetry data, your application logs and metrics indexes. Explicitly deny access to all other indexes, especially any security audit logs, HR data, or financial records. This principle of least privilege is non-negotiable. If the AI agent ever behaves unexpectedly or is compromised, the Splunk RBAC configuration is your last line of defense against a catastrophic data breach. Once the core MCP server is installed and the RBAC permissions are configured, you can extend the agent's capabilities significantly by installing the Splunk AI Assistant application. This is a companion app, also available on Splunkbase, that adds a suite of AI-specific tools to the MCP server's tool catalog. The most powerful of these is the Generate SPL tool. When the AI agent needs to answer a complex question about your telemetry data, it can call Generate SPL with a natural language description of the query it wants to run. The Splunk AI Assistant uses a built-in language model to translate that description into a syntactically correct, optimized SPL query. This is enormously valuable because writing efficient SPL requires deep expertise. The Explain SPL tool works in reverse. It takes an existing SPL query and generates a plain English explanation of what it does. This is invaluable for onboarding junior SREs who inherit complex, undocumented search queries. The Ask Splunk question tool allows the agent to query Splunk's official product documentation directly, enabling it to troubleshoot configuration issues without leaving the agentic workflow. Together, these tools make the AI agent a genuinely capable Splunk operator.
With the application installed and the service account configured with the correct RBAC permissions, the final configuration step is generating the authentication token. Tokens are the preferred authentication mechanisms for API integrations in Splunk because they can be scoped, rotated, and revoked independently without affecting the service account's password. Log into Splunk using the dedicated MCP service account you created, not your admin account. Navigate to your user settings by clicking on the account name in the top right corner, then select Tokens. Click the New Token button. Give the token a descriptive name such as MCP_server_token and set an appropriate expiration date. For production environments, a 90-day expiration with a calendar reminder to rotate is a reasonable policy. When you click Create, Splunk will display the token value exactly once. Copy it immediately and store it in a secure secrets manager, a password vault, HashiCorp vault, or a Kubernetes secret. If you close this dialog without copying the token, it is gone permanently and you will need to generate a new one.
This token is the credential that the MCP server will use to authenticate every search request it sends to Splunk on behalf of the AI agent.
Now configure Claude Desktop to use the Splunk MCP Server. Open the Claude Desktop configuration file. On macOS, this is at the path shown on screen in your application support directory. Add a new entry to the MCP Servers block. The command is npx mcp-remote, which uses the remote MCP client package to connect to your Splunk instance over HTTPS. Provide the endpoint URL, your Splunk web URL with the MCP path appended, and the authorization header containing your encrypted token using the bearer scheme. One important note, if your Splunk instance uses a self-signed certificate, you may need to set the node_TLS_reject_unauthorized environment variable to 0 for local testing. Never do this in production. Always use a properly signed certificate.
After saving the Claude Desktop configuration file with the Splunk endpoint URL and the bearer token, you must restart the Claude Desktop application completely. A full restart is required because Claude Desktop reads the MCP configuration file only at launch time. It does not hot reload configuration changes. Once Claude restarts, it will attempt to establish a connection to the Splunk MCP server and request the list of available tools. You can verify the connection status by clicking on the small Tools icon in the Claude Desktop interface, which opens the MCP Integrations panel. In this panel, you should see the Splunk MCP server listed with a green status indicator, confirming an active connection. Below the server name, you will see the complete list of tools that Claude has discovered and registered, such as Execute SPL, List Indexes, Generate SPL, and Explain SPL. If the connection fails, the panel will display a red error indicator with a message. The most common failure causes are a typo in the endpoint URL, an expired or incorrectly formatted token, a network firewall blocking the connection, or a TLS certificate validation error on the Splunk server. Each of these has a specific remediation path. With the full architecture connected, let us walk through a realistic agentic observability scenario from start to finish. Imagine your monitoring dashboard shows a spike in HTTP 500 errors on the checkout service. Instead of manually writing SPL queries, you open Claude and type, "The checkout service is showing elevated error rates. Investigate the root cause using our Splunk telemetry from the last 30 minutes." Claude processes this request and immediately invokes the MCP bridge. It calls Generate SPL to construct an optimized query targeting the OpenTelemetry index, filtering for the checkout service and status codes above 499. It then calls Execute SPL to run the search. Splunk returns the aggregated results. Claude analyzes the data and identifies that the errors are concentrated on a single database query, the one that fetches product inventory. It calls Execute SPL again with a more targeted query to retrieve the specific trace IDs associated with the failing requests. It correlates those traces with the corresponding log entries and identifies that a recent deployment introduced a missing database index. Claude presents this complete root cause analysis in plain English, with the specific trace IDs and the exact line of code that needs to be fixed. The entire investigation takes under 30 seconds. The agentic loop we just demonstrated is powerful, but it is still fundamentally reactive. The SRE had to notice the spike, open Claude, and type a question. True agentic SRE goes one step further. It closes the loop entirely. When an alert fires in Splunk, instead of paging a human, the system wakes up an automated agent that immediately begins the investigation and remediation workflow without any human intervention. This is not science fiction. It is a direct consequence of combining three technologies we have already built: the OpenTelemetry pipeline that provides structured, high-fidelity telemetry data, the Splunk MCP server that gives the AI agent programmatic access to that data, and the monitoring as code configuration that defines the exact thresholds and conditions that trigger the agentic workflow. The automated remediation agent does not replace the SRE. It handles the first 15 minutes of every incident, the triage, the initial diagnosis, the documentation, so that when the human SRE does engage, they are walking into a situation that is already partially understood and partially contained. This dramatically reduces mean time to resolution and eliminates the cognitive burden of 3 a.m. incident response.
The automated remediation architecture adds 2 new components to our existing pipeline. The first is a webhook trigger. When a Splunk alert fires based on the monitoring as code thresholds we defined earlier, instead of sending an email or a PagerDuty notification, it fires an HTTP post to a webhook endpoint. This webhook is the entry point for the automated agent. The second new component is the managed agent runtime. This is a persistent process running in a container or a serverless function that listens for incoming webhook payloads. When it receives an alert, it instantiates a Claude agent with a specific system prompt that defines its role, its available tools, and its operational boundaries. The agent receives the alert payload, which includes the alert name, the time range, and the initial metric values. It then uses the Splunk MCP Server to run a series of diagnostic queries, building a complete picture of the incident. Once it has identified the likely root cause, it uses a GitHub MCP server to read the relevant source code, generate a patch, and open a pull request. The entire workflow, from alert to pull request, can complete in under 2 minutes.
An AI agent operating in a production environment needs more than raw intelligence. It needs institutional knowledge. Every engineering organization has specific conventions, constraints, and procedures that are not documented in any public dataset. Which database should the agent restart first during a cascade failure? Which Kubernetes namespace is considered production versus staging? What is the maximum number of pod replicas the agent is allowed to scale to without human approval? Without this context, the agent will make technically correct but operationally inappropriate decisions. The solution is the runbook skill, a structured knowledge base embedded in the agent system prompt. The runbook skill is a carefully written document that defines your organization's standard operating procedures for common failure modes. It specifies the exact sequence of diagnostic steps for each alert type, the escalation thresholds that require human approval, and the hard constraints the agent must never violate. By providing this institutional knowledge as a system prompt, you transform a generic LLM into a specialized SRE agent that behaves consistently with your team's established practices. The runbook skill is the bridge between the agent's general reasoning capability and your organization's specific operational reality.
Autonomous agents should not have unchecked write access to production. The approval gate pattern enforces this. The agent workflow has 3 steps. First, the agent calls open_pull_request with the proposed fix. Second, the agent calls request_approval and waits. The session pauses. A human reviews the pull request and makes a decision. Third, and only if the human approves, the agent calls merge_pull_request. If the human rejects the change, the agent stops and reports. The merge_pull_request tool is never called without a prior approved response from request_approval. This is not a limitation of the system, it is the design. You decide what open_pull_request actually does. Your application handles the execution. The agent just calls the tool. Let's take a moment to appreciate what you have built today. You started with a Node.js application and added zero-code auto-instrumentation using a single -require flag. You deployed an OpenTelemetry Collector that scrubs PII using regex-based redaction before data ever reaches a backend. You configured the Splunk HEC exporter to route process telemetry into Splunk with proper token security and TLS enforcement. You defined your alerts as code using monitoring as code principles, making them version-controlled, testable, and AI-readable. You installed and configured the Splunk MCP Server, enabling an AI agent to query your observability data using natural language. And you explored the Claude Managed Agents pattern for autonomous incident remediation with a human-in-the-loop approval gate. This is not a theoretical architecture. Every component in this pipeline is available today. You can deploy it this week. Knowledge check. Question 1 of 5. When initializing the OpenTelemetry Node SDK programmatically in a common JS application, what is the correct way to set the service.name attribute? Think about it. The answer is on the next slide.
Did you get it? The correct approach is to pass a resource object to the Node SDK constructor using the semantic resource attributes .service_name constant as the key. Passing service name directly to the Node SDK constructor is a common mistake. It is not a valid top-level option and will be silently ignored. Always use the resource object.
Question 2 of 5. In an OpenTelemetry Collector pipeline, what is the correct ordering for the memory_limiter, redaction, and batch processors, and why? Think about it.
The correct order is memory_limiter first, then redaction, then batch. The memory limiter must be first to protect the collector process from out-of-memory crashes before any processing begins. The redaction processor operates on individual data points, so it runs next. The batch processor groups data points for efficient export, so it runs last. Reversing this order can result in either data loss from OOM crashes or PII reaching the export stage before redaction. Question 3 of 5. True or false? Regular expression patterns in the OTel Collector YAML configuration can be left unquoted without risk of parser errors. Think about it. The correct answer is false. As we covered during the redaction processor configuration, it is absolutely critical to wrap your regular expressions in single quotes within the YAML file. Regular expressions often contain special characters and \escape sequences, like \d for digits or \b for word boundaries. If you leave these unquoted, the YAML parser will attempt to interpret them as standard YAML syntax, which will result in parser errors or, even worse, silently corrupted regex patterns that failed to catch the PII they were designed to block. Always use single quotes for regex in YAML. Question 4 of 5. Which 3 saved searches.conf configuration keys are deprecated in Splunk Enterprise 9X and should be removed from alert definitions? Think about it. The 3 deprecated keys are alert_type, alert_comparator, and alert_threshold. In Splunk 9X, alert conditions must be defined entirely within the SPL search string using a pipe where clause. Using the deprecated keys may produce unpredictable behavior in newer Splunk versions. Always define your alert threshold logic in the SPL itself. Final question. What 2 RBAC capabilities must be assigned to a Splunk role to enable full use of the Splunk MCP Server, including token management? Think about it. The 2 required capabilities are MCP_tool_execute and MCP_tool_admin. The MCP_tool_execute capability grants permission to invoke MCP tools. The MCP_tool_admin capability grants permission to create and manage the encrypted authentication tokens that MCP clients use to authenticate. Both are required. Assigning only one will result in either failed tool calls or the inability to generate tokens. Thank you for watching. If you found this valuable, please subscribe to the Nextgen AI channel and hit that notification bell so you never miss an episode. Connect with Juan Achurra on LinkedIn to continue the conversation on agentic operations, SRE, and the future of intelligent systems. Until next time, keep building, keep learning, and keep pushing the boundaries of what's possible.